The ratio test. The ratio test states the following. It says, suppose you have a series, a sub n, with positive terms, and that L is the limit, as n approaches infinity, of a sub n plus 1 divided by a sub n. If this limit L is less than 1, then the series converges. If L is greater than 1, or if L is equal to infinity, then the series diverges. But if L actually equals 1, then the test is inconclusive, meaning it may or may not converge. If this happens, you'll have to try another test for convergence. When to use the ratio test? We can use the ratio test when the general term a sub n involves factorials, or nth powers. Now remember that n factorial is equal to n times 1 less than n times 2 less than n times 3 less than n, and so forth. This can be simplified to n times n minus 1 factorial. For example, 4 factorial is 4 times 3 times 2 times 1. That is 4 times 1 less than 4 times 2 less than 4 times 3 less than 4. 4 times 3 times 2 times 1 gives us 24. Also, before attempting to use the ratio test, be sure to check that the series has positive terms. Generally, you can look at a graph of the function that results when you replace the n's in the general term by x. Now we're ready to look at some examples. The directions here are to determine whether the series converges or diverges. Here we have the summation from n equals 1 to infinity of n divided by 2 to the nth power. If you look at the function that results when you replace the n's with x's, x over 2 to the x power, we notice that this function is positive on the interval from 1 to infinity. Generally, a graph could give us an idea. Since the function is positive, and since the general term contains a power of n, it might be a good idea to try the ratio test. We will begin by computing a sub n plus 1 divided by a sub n. Remember, a sub n plus 1 is what results when you replace the n in the general term with n plus 1. This gives us n plus 1 divided by 2 to the n plus 1. That is a sub n plus 1. And then in the denominator, we have a sub n, which is n divided by 2 to the nth power. When dividing two fractions, you have to multiply by a reciprocal. The reciprocal of n divided by 2 to the nth power is equal to 2 to the nth divided by n. We can split up the exponent in the denominator. 2 to the n plus 1 power is the same as 2 to the n times 2 to the first power. After simplifying, the 2 to the nths cancel out, leaving us with n plus 1 divided by 2n. Now we compute the limit as n approaches infinity. This gives us 1/2. Now since 1/2 is less than 1, recall from the theorem that if the limit is less than 1, the series will converge. Now we will look at another example. The directions here are to determine whether the series converges or diverges. Here we have the summation, n equals 1 to infinity, of n to the nth power divided by n factorial. Clearly, the general terms are positive since the index starts at 1 and the factorial function is non-negative. Since the general term involved a power of n and also a factorial, it might be a good idea to use the ratio test. We'll begin by computing a sub n plus 1 divided by a sub n. Remember, a sub n plus 1 is what results when you replace the n in the general term with n plus 1. This gives us the quantity n plus 1 to the n plus 1 power divided by n plus 1 factorial. Again, all of that is a sub n plus 1. In the denominator here, we have n to the nth power divided by n factorial. That is your a sub n. Now let's look in the numerator. The quantity n plus 1 to the n plus 1 power can be split up as n plus 1 to the nth times n plus 1 to the first. In the denominator, n plus 1 factorial is the same as n plus 1 times n factorial. After simplifying, the n plus 1's cancel and the n factorials cancel, leaving us with the quantity n plus 1 to the nth power divided by n to the nth power. Since both the numerator and the denominator have powers of n, we can condense this to be the quantity n plus 1 over n to the nth power. If you divide each term in the numerator by n, that reduces further to 1 plus 1 over n, all raised to the nth power. Now it's time to take the limit as n approaches infinity. If you take the limit as n approaches infinity of 1 plus 1 over n to the nth power, you get e. Since e is greater than 1, recall from the theorem that the series will diverge.